into a part of mathematics that's both incredibly deep and has a history shaped by some truly extraordinary figures. We're working with a talk from a math history series today, and it's really packed with insights.
Absolutely. Our deep dive today is all about the history of functional analysis, particularly the crucial period leading up to the transformative work of Alexander Grothendieck. Our goal is to pull out the most important threads from this history, understanding foundational ideas like norms and duality, and see how Grothendieck arrived and, well, in a sense, completely reimagine the landscape. What's great about the material you've shared is it focuses on the ideas and the human story, which makes it much more accessible than a purely technical analysis.
Definitely. So where did this whole story begin? What was happening in functional analysis before Grothendieck burst onto the scene?
The talk we're using really sets the stage, describing a prehistory phase, roughly from, say, 1920 to 1940. It acknowledges important groundwork laid earlier by names like Fréchet, Rez, and Hilbert, which you can find detailed in, say, the Bourbaki history notes. But the big turning point, the moment it became a general theory, was with Banach.
Banach, yeah, that name comes up a lot. What was it about his approach that was so foundational?
He brought this powerful axiomatic perspective. Instead of just proving isolated results, he built a framework based on simple core ideas. The material highlights two key concepts he really formalized and pushed forward. First, the idea of a norm.
Right, like a way to measure size, maybe for a function. Is that the basic idea?
Exactly. Think of it as length or magnitude, but applied to more abstract mathematical objects. But here is a crucial nugget the speaker emphasizes. There isn't just one way to define a norm. You can define many different norms on the same space.
Yeah.
And comparing them, understanding their relationships, finding the right norm for a particular problem, that's where a lot of the skill and creativity, the art of functional analysis, really lies. The talk even mentions how applying different norms comes up in analyzing Fourier's series, connecting it to the work of someone like Kant, who recently passed away.
Interesting. And the second big idea?
The second big idea from Banach, which is absolutely central and reappears throughout this history, is duality.
Okay, duality. We hear that term across math.
Yeah.
What does it mean specifically in this context? Like, what's the core concept here?
At its simplest, it's about looking at a space of objects like functions, maybe, and then looking at the space of continuous linear functions on those objects. Basically, how you can linearly map elements of your space to numbers while respecting the structure. Banach's great treatise essentially codified this program, laying out the core of what became known as the theory of Banach spaces. It was a perfect example of the axiomatic trend-sweeping math in the 1920s,
Right, axiomatizing everything. And this duality concept behaves differently depending on the space you're in, right?
Yeah.
I seem to remember it's kind of special in Hilbert spaces.
It really is, yeah. Hilbert spaces are spaces with an inner product, which gives you a natural notion of angle and length, generalizing Euclidean space. Hilbert originally defined them quite concretely, like sequences whose squares sum up, but von Neumann later gave the abstract axiomatic definition we use now, heavily motivated by quantum mechanics, his work on the foundations of quantum mechanics.
Okay.
The remarkable thing, the unique insight about Hilbert spaces, is that a Hilbert space is its own dual space.
Its own dual. How does that work?
There's a natural built-in way to identify elements of the space with elements of its dual. That's called a canonical isomorphism, basically a preferred natural map between the two. It's quite elegant.
Huh. So it pairs up perfectly with itself.
Exactly. Now contrast that with other important spaces, like the LP spaces functions where the pth power is integrable. For these, the talk points out a key theorem. The dual of LP is LQ, where 1p plus 1q equals 1.
Okay, so LQ isn't necessarily the same as LP.
Right. Unless P equals Q equals 2, which is the Hilbert case, LQ is a different space from LP. And this was a major conceptual hurdle in infinite dimensions, much more complex than in finite dimensions, where you can think of vectors and dual vectors as being essentially the same space, just maybe indexed differently, like in tensor calculus.
Makes sense. That difference is key.
Absolutely. And this era also saw Banach formalize the idea of weak convergence, building on earlier ideas from Hilbert. This is another twist of infinite dimensions. You have strong convergence, where the norm goes to 0, and weak convergence, where pairing with any dual element converges.
So like the coordinates converge, but maybe not the overall size.
Kinda, yeah. It's like saying components converge, but not necessarily uniformly or strongly. The source material notes this is crucial, especially for the calculus of variations, sometimes maybe underserved in teaching. There's a charming anecdote about Henri Cartan deflecting a question about it by just saying, "Oh, read the chapter in my father's book."
Huh. Classic academic deflection.
Pretty much. So yes, the takeaway from this prehistory is that duality in infinite dimensions was significantly more intricate and sometimes troubling than the finite dimensional case. And unlike finite dimensions, where the dual of the dual is always the original space, that isn't always true in infinite dimensions. The talk uses a great phrase to describe the dual of L1 space, which is L infinity. A monster.
A monster. I love that. It really captures the sense of unexpected difficulty and complexity. So that takes us to about 1940. Who else were the major players at this time besides the Banach school? Any other key figures?
Oh, absolutely. You absolutely have to include von Neumann again. His knack for axiomatics wasn't limited to Hilbert spaces. He applied it everywhere, from game theory to set theory. Just brilliant.
Right.
For our story, his big contribution was using Hilbert spaces to give quantum mechanics its rigorous mathematical foundation, unifying Schrödinger's waves and Heisenberg's matrices.
A synthesis. And he was busy with, well, everything else too, including computers, right? Johnny von Neumann, a fascinating figure.
Indeed. A true polymath. And then, across the Atlantic, the Russian school was incredibly active, with figures like Gelfand and Kolmogorov. They were publishing in German before the war, so they were very much connected with European math.
Okay, Kolmogorov. Probability, right?
Exactly. Kolmogorov is famous for his axiomatic formulation of probability, actually solving one of Hilbert's problems by using functional analysis techniques. He took Poincaré's ideas about probability depending on coordinate systems, things like Bertrand's paradoxes, and applied them to problems with infinite degrees of freedom.
Like infinite coin tosses.
Precisely. Moving probability theory from finite possibilities into a whole new realm, infinite dimensions.
And Gelfand.
Gelfand's early work, particularly on normed algebras, what we now call Banach algebras, was also groundbreaking. He discovered this deep connection between commutative Banach algebras and compact topological spaces via something called the spectrum, a term Grothendieck would actually borrow later. This duality between algebras and spaces was a really powerful insight.
So many connections already forming. Good. Okay, fast forward past the war. What did the landscape look like then, especially in France? Was there a resurgence?
There was a real surge, yes. A renewal in functional analysis in the post-war period, heavily centered at the University of Nancy. Dieudonné and Schwartz were kind of the anchors there, drawing others like Mackey, known for work linking topology and duality. And Ribbenboim, who was Brazilian, then moved to Canada.
Nancy seems like the place to be then.
It really was. And the personalities there were key. Dieudonné is described as the vital force, an imposing figure, radiating energy. The talk includes this funny detail that only a few people could talk to him without being, intimidated. He was a relentless advocate for the axiomatic method, Bourbaki style.
I can picture that.
And Velsart, the Bourbaki secretary and head of math at Nancy, connecting with engineering schools, which is maybe surprising given Bourbaki's reputation for pure abstraction. There's that vivid anecdote the speaker mentions about Delsart soldier comparing their wartime retreat to General Bourbaki's army being cornered near the Swiss border back in the Franco-Prussian War. Bit of historical color there.
All right.
And then there was Laurent Schwartz with his genuine stroke of genius, the theory of distributions.
Distributions. Yeah. Okay, how can we think about that simply? It sounds intimidating.
Well, at its heart, a distribution isn't really defined by its value at a point, like a normal function. Instead, it's defined by how it acts on nice functions, called test functions. It's a continuous linear form on a space of these test functions. So the very definition is rooted in duality, understanding these generalized functions by how they pair with other functions.
Okay, so it's defined by its relationships, its interactions. Was that idea completely out of the blue?
The speaker notes that Dirac actually had a definition that was nearly perfect for his famous delta function, using integration by parts to show how it acted on other functions. He kind of saw distributions as objects defined by their action.
So the seed was there.
The seed was there, intuitively. But Schwartz took this intuition and built a complete, rigorous, and incredibly powerful mathematical theory around it. That work earned him a Fields Medal.
Wow. And Dieudonné was involved here too?
Yes, Dieudonné played a crucial role. Apparently, the first version of Schwartz's book on distributions needed stronger topological foundations. Dieudonné really pushed Schwartz to make those rigorous, which led them to collaborate on duality theory for spaces beyond just Banach spaces. Spaces von Neumann had introduced, but not deeply developed, called locally convex spaces. Their joint paper on duality in F and LF spaces was a major piece of work setting the stage.
Okay, so that sets the stage perfectly. An incredibly active scene in Nancy. Now, where does Grothendieck enter this picture?
Grothendieck arrived right around this time in the late 1940s. And his background is really essential to understand him, as the talk highlights quite strongly. He was a stateless refugee from Ukraine, deeply affected by his father's tumultuous revolutionary life bouncing between prisons, involved with Makhno's anarchist army in Ukraine, the Spanish Civil War. Just an incredible, difficult history. The speaker suggests this difficult, stateless existence contributed significantly to his later radical path, seeing him almost as a delayed victim of Hitler. It's a powerful piece of context from the source material, presented very factually.
That's quite a background. Hard to imagine.
Absolutely. But despite this, his early talent was just astonishing. In Montpellier, essentially self-taught, he rebuilt major pieces of foundational math, like the Lebesgue integral, doing it his own generalized way, almost from scratch. When he came to Paris, he attended Parten's seminar. He claimed later he didn't understand anything, but the speaker in the talk suspects that was probably a bit of a bluff.
Maybe some false modesty, or just a different way of thinking.
Could be. His personality was famously intense, described colorfully in the source as an uneducated wild dog compared to the very formal Mr. Professor Carton.
That's quite a description.
It paints a picture, doesn't it? So, recognizing his raw genius, but perhaps seeing the personality clash, Carton sent him to Nancy to work with Dieudonné and Schwartz, hoping they could guide his immense talent.
Made sense. Send him to the experts in the field he was gravitating towards.
Exactly. And this is the moment of legend. Dieudonné presented him with a list of 14 difficult open problems from the end of their big duality paper. Crucially, telling him not to rehash known results, but to do something new. Just solving one of these problems would have been a major feat at the time.
Right. And this is where the famous story comes in, isn't it? Dieudonné shouting across the building.
Yes. The anecdote, which seems quite well known, is that Dieudonné yelled down the hallway or across the building to Schwartz, "Il a tué l'analyse fonctionnelle." He killed functional analysis.
He killed it. What did that mean?
It sounds dramatic, maybe even negative, but the insight here, as the talk explains it, is that in this burst of extraordinary productivity and abstraction, Grothendieck had seemingly solved all those problems. He'd pushed the theory in that specific direction, the direction of duality and locally convex spaces, as far as it could go at that moment. He'd sort of completed that particular program.
Wow. Not killed, but completed. Brought it to a kind of conclusion.
Precisely. And just a fascinating personal detail mentioned, Grothendieck was apparently quite a good pianist and played at Schwartz's house sometimes. Despite living in poverty at the time, he even rented a piano for himself. A real contrast between the austere abstract thinker and the musician.
That adds another layer. So what were the specific ideas in his thesis that prompted such a strong reaction and sort of completed that line of inquiry?
The core of his thesis, his groundbreaking work, involved two profound concepts: topological tensor products and nuclear spaces.
Okay, topological tensor products. What was the motivation there?
It came partly from Schwartz's kernel theorem, the idea that many linear operators between function spaces can be represented by a kernel, which is itself a distribution. This hinted at a connection between operators acting between spaces and ways of combining the spaces themselves, which naturally leads you to think about tensor products. Schwartz essentially posed the challenge: build the right kind of tensor product for these functional analysis spaces, one that properly incorporates the topology, the structure of the spaces.
Okay, find the right way to multiply spaces.
Sort of, yes. And Grothendieck's initial discovery, as the speaker notes, was almost a surprise, maybe even a slight disappointment at first glance. He found two distinct natural ways to define this topological tensor product, what he called the pi and epsilon tensor products.
Two, not just one answer.
Exactly, two. Which one do you want, was the implied question. A bit awkward.
Yeah.
But this actually led him to the key insight of nuclear spaces. Maybe for certain very special spaces, these two different tensor products would actually coincide. They'd give the same result. These would be the nuclear spaces. They turn out to be precisely the nice spaces where things like the kernel theorem behave particularly well and cleanly from this abstract tensorial perspective.
Ah, so the problem led to a new class of objects where the problem vanished.
That's a good way to put it. His thesis was incredibly deep and dense. It rigorously defined these two tensor products, explored their properties, including how they interacted with duality, that crucial concept again, and how they behave structurally. their functorial properties, how they preserve structure under mappings. The talk mentions that Shapton had done some related earlier work on cross norms, and Grothendieck's two norms turned out to be the smallest and largest reasonable ones you could define.
Did Grothendieck build on Shapton?
Characteristically, Grothendieck hadn't read Shapton's work. There's that famous anecdote about him later at IS saying, "Here we don't read, we write."
Right, the legend of him not reading others' work.
But his scope was vastly broader than Shapton's anyway, which was mostly focused on Hilbert spaces. Grothendieck was working in much greater generality.
Makes sense. Didn't his thesis end with a famous conjecture?
Yes, at the end of his thesis, he posed a famous conjecture about compact operators being approximable by operators of finite rank, showing it was equivalent to something like 34 different conditions, a huge web of connections. The interesting twist is that this major conjecture, central to the theory, was later disproven about 15 years after his thesis.
Disproven? How?
By what the speaker calls a very silly counterexample, something quite simple involving basic Hilbert space operators constructed by Pert and Flow. It shows how even deep structural theories can sometimes stumble on relatively simple cases.
Fascinating. How a conjecture at the heart of such deep work could be undone by something seemingly simple later on. So, how did this abstract functional analysis work then connect to other parts of mathematics? Did it stay isolated?
No, not at all. And this is where you see the true power of his abstract viewpoint. It built bridges. The talk highlights connections to complex analysis and algebraic geometry, particularly through the work of Cartan and Serre, who were developing sheaf theory, Grothendieck's vectorial Kenneth theorem, which is a result about how tensor products of chains of nuclear spaces behave nicely under certain operations, was a crucial tool. It was used apparently quite effectively to prove what was known as Dolbeau's theorem, or conjecture at the time, a fundamental link between different ways of measuring holes in complex manifolds, different cohomology theories. This was a major step forward, driven by his abstract machinery.
So his tools were immediately useful in other cutting-edge areas.
Exactly. And we also see Gelfand re-enter the story here from a different angle. Gelfand later realized that Grothendieck's nuclear spaces were exactly the framework needed to build a rigorous theory of integration and probability in infinite dimensions.
Infinite dimensions again. Why was that needed?
This was directly motivated by physics, specifically Feynman's path integrals in quantum field theory and the mathematics of Brownian motion. These involved integrating over infinite dimensional spaces of paths or fields. Gelfand became a huge advocate for nuclear spaces in this context, developing things like random distributions. Key theorems, like extending the Bachner theorem, which connects positive definite functions and measures via Fourier transforms to infinite dimensions, were proven on nuclear spaces. This was done by people like Minlows and Fernique, sometimes independently due to, communication difficulties between East and West at the time.
Right, the Iron Curtain era.
So Gelfand's work, looking for tools for physics applications, directly intercepted with Grothendieck's abstract theory, showing its unexpected applicability.
That's a great convergence.
The talk also briefly mentions Grothendieck's abstract theory of Fredholm determinants in his thesis, which Serre later applied successfully in a completely different area, the study of Paddock-Banach spaces. More bridges.
So after this incredibly fertile period in functional analysis, publishing the thesis, what came next in his journey? He didn't stay focused just on this.
No, he moved on relatively quickly. His thesis was defended in 1953, but not published until 1956. As we mentioned, he wasn't French, yet he only became French much later in 1971. Reportedly, he might have declined citizenship earlier, perhaps to avoid military service obligations associated with it then. This statelessness meant he didn't immediately get a permanent French academic post, despite his obvious genius.
But what did he do?
Well, like several other prominent French mathematicians before him, Weil, Dieudonné, Schwartz himself, he spent a couple of years abroad, in Brazil, specifically Sao Paulo, from about 53 to 55.
Brazil, was he productive there?
Incredibly productive, yes. He gave courses on topological vector spaces, which became influential notes, and wrote major papers, some apparently incredibly complex and difficult. The speaker mentions Pizier would talk about these later, and the speaker brings back that il a tué l'analyse fonctionnelle, quote, in this context, suggesting that his work, by completing that phase of duality theory, kind of cleared the way. It brought a sense of closure to that particular line of development, allowing focus to shift.
So Brazil marked a turning point.
It really did. This period in Brazil was fundamentally a transition to his second monumental phase, his work on algebraic geometry. He laid out his revolutionary new program, the Theory of Schemes, at the 1958 International Congress of Mathematicians in Edinburgh. And that just exploded into an immense body of work very, very rapidly over the next decade.
A whole new mountain to climb. And of course, his life took another significant turn later on, didn't it? Moving away from mainstream math.
Yes, absolutely. Towards political and ecological activism, starting around 1970 and intensifying afterwards, leading him to eventually withdraw completely. And the speaker in the source talk concludes this historical account with a really poignant observation. He mentions finding modern anarcho-ecological communities in the Ardèche region of France. These are people building collective farms, trying to live self-sufficiently off the land, embodying a spirit that feels connected to Grothendieck's later ideals of simple living, anti-militarism, and ecological harmony.
Even if they don't know his name or his math.
Exactly. Even if they know nothing of his mathematical work or his specific history, they are, as the speaker puts it, building something concrete, not just abstract theory. It's compared to the spirit of the early kibbutzim, maybe, suggesting that Grothendieck's ultimate dream or ideal, in some form, isn't dead. It lives on in these unexpected ways.
That's a powerful image to end his story with. What an incredible journey we've taken through this history, really. From the foundation's binaclade, through the axiomatic developments, the power of duality in distributions, right up to Grothendieck's radical reframing with tensor products and nuclear spaces, concepts that didn't just perfect one area but built bridges across complex analysis, geometry, and even into probability in physics. It's quite something.
It really is, and what an illustration of how foundational mathematics, sometimes developed from extremely abstract principles, can have these deep, unforeseen connections to concrete problems in other fields entirely. Grothendieck's unique ability to rebuild things from scratch, starting from the most general principles, is just a defining feature, isn't it? And it contrasts so sharply with the very human, complex details of his life and journey.
It really leaves you thinking about the different ways truly groundbreaking ideas emerge. Sometimes it's careful, cumulative building on predecessors step by step. Sometimes it's finding just the right axioms to capture something essential. Sometimes it's pure intuition applied to a difficult problem. And sometimes, like maybe with Grothendieck, it's a radical, almost overwhelming abstract vision, or rebuilding from the ground up, sometimes even by intentionally not following the existing paths, not reading the literature in the conventional way. How does that impact the very shape of the knowledge that follows? It's a big question.
It is, and the way ideas live on, sometimes in unexpected forms, maybe even beyond the intentions or the specific field of their creator. Well, as the talk reminds us, perhaps his ideal isn't dead, something to ponder.